Human beings like to think they're unique, and much of our understanding of life is built on that idea. We measure everything in relation to ourselves. But the universe doesn't necessarily follow our scale or our rules. If there's one thing that truly measures existence, it's not people, it's time. Without time, nothing could exist. Time is the one constant. Think of a river. From far away, it looks like one long flow, steady and continuous. But if you watch closely, you will notice it's never the same though. Water you see now is gone a moment later, replaced by new water rushing past. As Heraclitus said, you cannot step into the same river twice. That's much like time. Each moment passes and never returns. Einstein showed us that time isn't fixed either. It can stretch or slow depending on speed and gravity. Near the speed of light, time moves slower. Near a black hole, it almost stops altogether. What we think of as a steady current is actually flexible and sometimes nearly frozen. But why does time always seem to move forward and not backward? This puzzle was explored during the Industrial Revolution, when steam engines powered factories and trains. Engineers noticed that no matter how well machines were built, they wasted heat. Rudolf Clausius realized that energy always spreads from hot to cold, and never the other way around. This insight became the second law of thermodynamics. Clausius explained that energy naturally becomes less ordered, a principle called entropy. Once energy spreads, it can't return to its exact original state. Imagine 100 marbles, half red and half blue, perfectly separated in a box. Shake the box, and the marbles scatter randomly. The order is lost. By chance, they'll never sort themselves back. That's entropy. Once order turns to disorder, it won't reverse on its own. Entropy is also what gives time its direction. We remember the past when things were more ordered, but the future is unknown because entropy always increases. Think about hot coffee. Cools as its heat spreads into the air. That heat won't suddenly jump back into the cup. Or crack an egg. Once broken and cooked, it can't return to its original form. This is why time always moves forward, because entropy does. For most of history, though, people didn't think about entropy. They thought about cycles, sunrise and sunset, the phases of the moon, the changing seasons. Time was tied to nature. Ancient Egyptians, for example, lived by the rhythm of the Nile floods. When Sirius appeared in the sky, it signaled the river's rising waters and the start of a new year. They created one of the first solar calendars with 365 days divided into 3 seasons: Akit flood, Pere planting, and Shemu harvest. They also built sundials to mark hours with shadows and water clocks that dripped steadily through the night. To them, time wasn't just practically, it was sacred, linked to rituals and the cycles of life. Centuries later, in 13th century Europe, the first mechanical clocks began ringing from church towers. They weren't precise by modern standards, but they made time public. Instead of being guided only by nature, people now lived by the tolling of bells. This marked the beginning of time as we know it today, not just natural, but measured and structured. For centuries, bells simply marked the passing hours. But real change came in the 17th century with Christian Huygens, a Dutch scientist. Fascinated by the steady motion of the planets, the moon, and the stars, Huygens believed the universe followed a grand mechanical rhythm. Sundials and water clocks of his time were crude, often drifting off. Huygens asked, what if a clock could match nature's precision? His breakthrough came from studying pendulums. He noticed that no matter the swing's size, pendulum always took the same amount of time to complete a cycle, a property called isochronism. In 1656, he built the first pendulum clock, accurate to within 10 seconds per day. Incredible leap forward. Around the same period, Isaac Newton was laying the foundation of classical mechanics. In his Principia, Newton described time as absolute flowing uniformly, unaffected by anything external. To him, the universe was like a stage where planets, stars, and objects obeyed strict laws of motion. Space was a fixed grid, and time was an invisible line moving forward second by second. His equations predicted everything from a falling apple to the orbit of planets with astonishing precision. For centuries, Newton's vision of an unchanging clockwork universe dominated science. But Rudolf Clausius added a new twist. In studying heat and engines, he discovered entropy, the tendency for energy to spread out and disorder to increase. This became the second law of thermodynamics, unlike Newton's timeless backdrop. Clausius revealed time's direction. Order gives way to disorder, making processes irreversible. A hot drink cools. An egg crack entropy ensures the arrow of time always points forward. Then came Albert Einstein. As a boy in Germany, he was more interested in daydreams than rote schooling. He began to wonder what if time wasn't fixed. In 1905, working in a Swiss patent office, he introduced the special theory of relativity. Einstein showed that space and time weren't separate, but part of a single fabric: space-time. Movement through space could affect time itself. The faster you travel, the slower time passes for you. This leads to the famous twin paradox. Two twins, Alice and Bob. Alice travels near the speed of light to a distant star and back, while Bob stays on Earth. When she returns, Alice is younger than Bob. Time is stretched differently for each. This wasn't just theory. In 1971, Joseph Haffel and Richard Keating tested it using atomic clocks on commercial airliners. They flew for cesium clocks around the world. When compared to clocks on Earth, the airborne clocks showed measurable differences, exactly as Einstein predicted. Both speed and altitude caused time to tick differently. These results became essential for modern life. Take GPS, for example. Satellites orbit about 20,200 kilometers above Earth at speeds near 14,000 kilometers per hour. Each satellite carries an atomic clock, but without accounting for relativity, GPS would drift miles off target within a single day. Special relativity predicts the clocks run about 7 microseconds slower each day due to motion, while general relativity predicts they run about 45 microseconds faster because they reef farther from Earth's gravity. The net effect is 38 microseconds faster per day compared to ground clocks. It may sound tiny, but GPS accuracy depends on perfect timing. Thanks to corrections from Einstein's theories, your phone can guide you within meters anywhere on Earth. Without them, navigation errors would quickly grow by miles. Satellites rely on extreme accuracy. If the satellite clock drifts even slightly, GPS signals become unreliable. Without corrections for relativity, GPS errors would grow by about 10 kilometers or nearly 6 meters each day. To fix this, engineers constantly adjust satellite clocks for both their high speed and weaker gravity at altitude. But while we've solved those timing issues, a new challenge appears on Earth itself. Our planet's rotation is not perfectly steady. Over time, tidal forces and other effects slow it down. Meanwhile, atomic clocks stay extremely precise. Mismatch grows, and to fix it, scientists add what's called a leap second to Coordinated Universal Time (UTC), usually added in June or December. This keeps our clocks in sync with the sun. Here's the problem. Computers aren't built to handle a second repeating or disappearing. When a leap second was added on June 30th, 2012, major sites like Reddit, Mozilla, and LinkedIn went down because their servers couldn't process the extra second. Financial systems also felt the shock, since trading depends on precision down to the millisecond. To avoid chaos, engineers created leap smearing. Instead of adding 1 second all at once, companies like Google gradually stretch out seconds over a full day. This smooth adjustment prevents crashes and keeps systems running. But what if time itself could do more than stretch? What if, under extreme conditions, it could freeze? That very idea fascinated young physicist Kip Thorne in the 1960s, after earning his PhD at Princeton. He met John Archibald Wheeler, who introduced him to black holes, regions where gravity is so intense it warps space and time itself. Thorne became one of the leading figures in understanding how gravity affects the flow of time. Einstein's theory showed that the closer you are to strong gravity, the slower time runs. Near-Earth atomic clock experiments confirm this effect. But near a black hole, the distortion is extreme. To a distant observer, someone falling into a black hole appears frozen at the edge, the event horizon. But to the falling person, time continues as normal, until they approach the singularity, where physics, as we know it, breaks down. This leads to another mystery. What happens to the information about everything that falls in? Stephen Hawking showed that black holes radiate energy and can evaporate, raising the fear that information could be lost forever, something quantum physics says is impossible. Physicist Gerard T. Hooft proposed that the information might not vanish, but could be stored on the surface of the black hole itself, like data etched into a two-dimensional sheet. Leonard Susskind later expanded this into the holographic principle. It suggests that everything inside a region of space, including the flow of time, could be encoded on its boundary. Like a hologram projecting a 3D image from a flat surface, this radical idea reshapes how we think of time. Instead of a river flowing from past to future, time may be a structure where all moments past, present, and future coexist at once. Some physicists describe this as the block universe, where every event is fixed within space-time, and our sense of time passing is just our way of moving through it. Time may not be what we think it is. Some scientists argue there's no true present moment. Instead, every moment past, present, and future exists together in what's called the block universe. In this view, the future is already fixed, just like the past, which raises tough questions about free will. If time is just another dimension of space, then what we see as choice may only be our experience of moving along a path that's already set. Physicists, such as Sean Carroll, have explored how this idea connects with quantum mechanics and cosmology. To us, time seems to flow and choices feel real. But on a deeper level, every event, births, deaths, and decisions is just another point in space-time, all existing at once. One thinker who took this even further was Julian Barbour. Unlike most academics, he worked independently in the Oxfordshire countryside, supporting himself as a translator while developing radical ideas about time. His doubts began in the 1960s while studying Einstein's relativity and quantum mechanics at the University of Cologne. Relativity showed him that time is just a coordinate in space-time, not something that flows. Quantum theory, meanwhile, treated time as a parameter in equations, but gave results that seemed random when observed. Barbour wondered if the real issue was not the theories themselves, but how they used time. Inspired by John Wheeler, he shifted focus away from the idea of time flowing and toward the idea of configurations, arrangements of the universe at any instant. Barbour called this timeless collection of possibilities Platonia. In this framework, time does not exist as a flow. Instead, each configuration, what we call a now, contains records that make it look like they're essay past. What we see as the arrow of time may just be patterns of information built into certain states. In 1999, Barbour published The End of Time, presenting Platonia to a wider audience. In it, he argued that every possible arrangement of the universe exists timelessly, like cards spread across a table. There's no inherent order. Time is something we create by mentally linking certain states together. What feels like progression is simply our minds arranging these nows into a sequence. Platonia also explains why time seems to move only forward. Physics equations usually work both ways, forward and backward, but in daily life, we see one direction. Glasses shatter, but Dante reassemble. Barbour suggested this arrow of time emerges only in regions of Platonia, where complexity increases, like our universe evolving toward greater structure. Beyond physics, humans have always wrestled with two different kinds of time. The Greeks called them chronos and tempus. Chronos is clock time, the measured, relentless ticking of seconds. Tempus is personal time, the way minutes can fly during joy or drag during stress. While clocks treat time as uniform, our brains stretch and compress it depending on focus, memory, and emotion. Neuroscience shows that even our sense of now is delayed. The brain takes milliseconds to process signals, meaning what we experience as the present is already in the past. Experiments like those of Benjamin Libet in the 1980s found that brain activity for decisions began about 300 milliseconds before people became aware of choosing. This suggests our awareness lags behind unconscious processes. Other studies reveal how the brain binds events closer together in time than they are, making cause and effect feel more immediate. Our sense of time also changes with emotion. During danger, for example, the brain's amygdala sharpens memory, making moments feel longer. In everyday life, this explains why time races when we reabsorbed and slows when we rebored or afraid. Taken together, psychology and physics point to the same idea. Time as we experience it is a construction. The brain stitches sensory signals, fills gaps, and builds the illusion of flow. Meanwhile, physics suggests that time may not exist fundamentally at all, only static states or configurations that we interpret as change. So what is time really? If every moment is fixed, then our lives are already written in space-time. But even if time is an illusion, it remains central to human experience. It shapes how we make choices, build memories, and live with meaning. Whether time exists independently or not, what matters most is how we use the moments we feel we have, right here, right now.